Hey everyone, welcome back to Chem Story. Today, we're diving into one of the most important concepts in chemistry, the octet rule. This rule helps us understand why atoms behave the way they do when they form chemical bonds. It's simple, but incredibly powerful once you really get it. All right, let's think about this for a moment. Why do atoms form chemical bonds? Atoms form bonds to reach a more stable state. And that stable state often looks a lot like the electron configuration of noble gases. That's where the octet rule comes in. So what exactly is the octet rule? It says that atoms tend to fill their outermost electron shell with 8 electrons to become chemically stable. A full outer shell, just like noble gases have, makes an atom more stable and less likely to react. But of course, there are exceptions. Elements in group 1, like hydrogen and helium, follow what's called the duet rule. Instead of 8, they're stable with just 2 electrons in their outer shell. Now, why is the octet rule such a big deal in organic chemistry? Well, it plays a fundamental role in explaining why atoms form specific types of bonds, especially covalent bonds, which are essential in building organic molecules. It also helps us predict what a molecule might look like and how stable it might be. By knowing how atoms share or transfer electrons to complete their outer shell, we can figure out the structure of a compound before we even draw it. And there's more. Understanding the octet rule helps us analyze how molecules react. It gives us a way to predict how bonds form, how they break, and what kind of chemical changes might happen. This is especially important in organic chemistry, where things like functional groups and reaction mechanisms all depend on how electrons are arranged and how stable those arrangements are. So then how do atoms actually achieve an octet? Well, there are 3 main ways they can do it. They can lose electrons, gain electrons from another atom, or share electrons with other atoms. Each method helps them reach that stable, full outer shell. Let's start with the first way, losing electrons. This is one of the most common ways atoms get to an octet, especially for certain types of elements. This happens a lot with metals, particularly those in groups 1 and 2 on the periodic table. When these atoms lose electrons, they form a positively charged ion, which we call a cation. Let's take a look at an example, sodium. Sodium has just 1 electron in its outermost shell. To become more stable, it loses that electron and forms a sodium ion, Na+. And by doing that, it ends up with the same electron configuration as neon, a noble gas in the second period. Another good example is magnesium and aluminum. Magnesium achieves stability by losing 2 electrons, which gives us a magnesium ion, Mg2+. Aluminum, on the other hand, loses 3 electrons, forming an aluminum ion, Al3+. In both cases, these atoms reach a noble gas electron configuration by simply giving up the right number of electrons. Now, another way atoms can achieve an octet is by gaining electrons. Instead of losing them like metals do, these atoms become stable by adding electrons to their outer shell. This mostly happens with nonmetals, especially those in groups 16 and 17 of the periodic table. These elements tend to gain extra electrons to fill their outer shell, and when they do, they form negatively charged ions, which we call anions. Let's take chlorine as an example. Chlorine has 7 electrons in its outermost shell, so it only needs 1 more to complete its octet. When chlorine gains that 1 electron, it becomes a chloride ion, Cl-, which is much more stable. And just like that, it takes on the electron configuration of argon, a noble gas in the third period. That's what gives it its stability. Another great example is sulfur. Sulfur has 6 valence electrons, so it needs 2 more to reach a full octet. When sulfur gains 2 electrons, it forms a sulfide ion, S2-. This gives sulfur the same electron configuration as argon, making it more stable, just like we saw with chlorine. In addition to losing or gaining electrons, atoms can also achieve a stable octet by simply sharing electrons. This is the third major way atoms reach stability. And this idea is especially important when we talk about carbon, a key player in organic chemistry. Carbon has 4 valence electrons, which means it needs 4 more to complete its octet. But instead of losing or gaining electrons, carbon forms covalent bonds by sharing electrons with other atoms. That's how it builds such a huge variety of stable compounds. A great example of this is methane, CH4. In methane, carbon shares 1 electron with each of 4 hydrogen atoms, forming 4 single covalent bonds. Through this sharing, carbon reaches a full octet, and each hydrogen atom gets a stable duet, following the rule for hydrogen stability. Now, while the octet rule is a super useful guideline, not all elements follow it perfectly. There are some important exceptions, and one of the most common is called the incomplete octet. Some elements, especially those with only a few valence electrons, just don't have enough to reach 8, even after bonding. Instead, they form stable compounds with fewer than 8 electrons in their outer shell. Let's take beryllium as an example. Beryllium has just 2 valence electrons, and in a compound like beryllium chloride, BeCl2, it forms bonds with only 4 electrons around it, not 8. Still, beryllium chloride is a perfectly stable compound. Another classic example is boron. Boron has 3 valence electrons, and in a compound like boron trifluoride, Bf3, it ends up with only 6 electrons in its outer shell. Even though that doesn't meet the octet rule, boron trifluoride is still a stable compound. Another major exception to the octet rule is something called the expanded octet. Some elements can actually hold more than 8 electrons in their outer shell, allowing them to form compounds that go beyond the standard octet. This usually happens with elements in period 3 or higher on the periodic table. And why is that? It's because these elements have access to the d orbitals, which give them extra space to hold more electrons. Let's take phosphorus as an example. In a molecule like phosphorus pentachloride, PCl5, phosphorus forms 5 bonds, which means it holds 10 electrons in its valence shell, not just 8. Another great example is sulfur. In sulfur hexafluoride, SF6, sulfur forms 6 bonds, holding a total of 12 valence electrons. So while the octet rule works well for many elements, those in period 3 and beyond can expand their octet, and that lets them form a wider range of stable compounds. These are just a couple of important exceptions, but understanding them is key when studying chemical bonding, especially in both inorganic and organic chemistry. Alright, so let's quickly wrap things up. Today, we explored the octet rule, a key idea that helps explain why atoms bond the way they do. We learned that atoms become stable by losing, gaining, or sharing electrons to complete their outer shell. We also talked about a few exceptions, like the duet rule, incomplete octets, and expanded octets found in elements from period 3 and beyond. Understanding these patterns is essential for making sense of chemical bonding, especially in both organic and inorganic chemistry. That's it for today's lesson. Thanks for joining me, and I'll see you next time on Chem Story.